This diagram illustrates the 5G network architecture. In this video, I will demonstrate how to use TESSERACT's data modeling and orchestration tool to transfer 5G standards into a real-life database blueprint, an object model graph for the radio access network. This graph is extremely simple and effective due to its object-oriented nature. In contrast, a conventional database schema would appear more complex than the SIM graph, with implicit relationships set to visible. Today, let's demystify the mobile operator's network, commonly referred to as 4G or 5G. I have some gadgets here representing key components of the network. First, we have the cell tower, which houses the antenna unit. In reality, multiple antenna units are typically mounted on a single tower. Each is connected to a remote radio unit via a feeder cable. Here, I have used a Lego piece to represent the remote radio unit. The remote radio unit contains optical modules, which connect to a fiber optical cable. In real deployments, this is usually a rugged block outdoor fiber cable containing multiple fibers. It runs all the way to optical modules on the baseband unit, commonly referred to as the base station. The antenna and the remote radio units are usually co-located or positioned close together, while the baseband unit can be several hundred meters to over a kilometers away from the remote radio unit. The antenna unit emits and receives radio waves, which are exchanged between the antenna and our mobile devices. When the antenna receives signals, they are passed to the remote radio unit, where they are converted from analog to optic signals, then transmitted over fiber to the baseband unit. The baseband unit processes these data packets and sends them to the backhaul network via a passive optical network. The PON is a wide area network that connects multiple base stations and cell sites to the core network. If you haven't heard of a radio access network, you've probably heard of a cellular network. They refer to the same concept. The term cell comes from the hexagonal shape found in a honeycomb. Each cell covers a geographic area and operates on a specific set of radio frequencies. Cells are arranged in a hexagonal pattern to optimize area coverage and minimize interference. Here, we have two hexagons representing two cells, each centered around a cell tower. Each tower has its antenna arranged either 120 degrees or 60 degrees apart, creating sectors that divide coverage areas. Cells from different towers overlap to ensure continuous connectivity. As we move, our mobile device communicate with multiple antennas and seamlessly hand over from one cell to another. Next generation antennas, often called smart antennas, can perform beamforming. Here is an illustration of beams formed by 1, 2, and 4 antennas. Using an antenna array, radio signals can be steered directionally rather than being broadcast omnidirectionally within the sector. This is a 2D representation, but in 3D, beam shapes resemble more complex volumetric patterns. Since I don't have a specific 3D diagram for radio antennas, I've used a microphone spoiler pattern for illustration. In reality, things are more complex. Buildings and terrain can block or reflect radio waves, which may cause signal degradation or coverage gaps.
Can I ask which materials reflect radio waves?
Walls and the ground can both reflect radio waves. 4G and 5G operate at different frequencies. Some wavelengths have a stronger ability to penetrate walls or diffract around obstacles, while others are less effective in this regard. To address this, operators deploy different frequency bands depending on the specific application and coverage requirements. How do we model and manage the RAN? Here's a diagram created with the TESSERACT data modeling and orchestration tool. As you can see, there are corresponding models for the radio unit, 那么同样的，我有天线单元，那么这个
Antenna
天线呢
unit,
就对应到我的这个东西，对吧？然后我的这个后面呢还有这个基站哈，我的基站呢可以用这个来代表啊，这就是我的基站。
and the baseband unit.
基站中间呢它是通过
In
这
this
些光
model,
模块
the baseband unit is connected to the antenna
把
unit
它连接
via
在一起。
optical
那么
modules.
这样子来看的话，我们是不是可以通过一个抽象的逻辑的
Using the
来
tesseract
很
tool,
容易的
we
描述
can
它们之间
accurately
的
reproduce the
连接或
physical
者
and
说是
logical
互关系。
structure of the
通过
RAN.
这种方式呢，我们
This
就可以很容易
topological model and
来
relationship
描述
graph
对运营商
describes the specifications, configurations, and data formats of the network elements.
和它传输的数据来进行一个管理和监控。通过我们的数据
Our
编排
tool
工具，
allows for
我们可以快速地
object-oriented
对
data
运行
modeling of
那么
network
我们试一
elements
试。
and their
首
relationships.
先我们从天线开始，
Let's start with the basic components.
天线单元、
Antenna unit,
射频单元、
radio unit,
分布式单元、
distributed unit,
集中单元。
centralized unit.
那么现在呢，我们
Now we
需要把
define
这
the
个关系，
relationships.
这就形成了
These form the
我们现
foundation
在
of
的
the
一个
radio
结构。
access
那么
network.
大家看到的这个呢，它是
In
一个
5G, the antenna and radio
基
units
标
are
的。
typically
那么
integrated
在
into a
5G
single
里面，
device
一般来说呢，
called
天
an
线单
active
元和射频
antenna
单元
unit.
它会合二为一，成一个设备。有源
Active antenna unit.
那么在 4G
In
里面，
4G, the
传统基站
baseband
呢
unit includes
它
both
实
the
际上是分布式
distribution
单元
unit
和
and the
基带
centralized unit.
基带处理单元。
Baseband unit.
那么按照刚才的说法呢，
The
这里有
active
一个天线
antenna
单元
unit
呢，它
model
是
inherits from
在这
both the
个
antenna
天线
unit
单元
and the
和射
radio
频单元
unit
的一个
models.
所以它是一个
Similarly,
关系。
the baseband unit model inherits
同样的，基
from
带处理
both
单
the
元呢，就是
distributed
在
unit and the centralized
就是
unit
在这个
models,
自身
meaning it inherits
那么
all
这样
their
子的话呢，
respective
这个代
attributes.
表的意思呢，就是说这个基带处理单元呢，它会具有分布式单元和集中处理单元的所有属性。这里呢，我有一个已经建好的模型。
Here is the complete
首
object
先呢，我
model
们
graph.
把这些
Let's now
相
hide
关的
any
参考
unrelated reference models
给它
to
整理起
better
来。
focus on the core structure of the RAN, which is made up of the master data models.
整理完了以后呢，我们现在看到的呢，就是一个比较
The
初步
Node
的
B
一个
model
模
represents
组
the
大概
logical
它这是我们的主
configuration of
数
a
模
base
型。那
station.
么在这个主数
We
模
can
型里面
delve
呢，
deeper
我们可
into
以看
the
到
Node B
有我们
model
基站，
to
我们也
explore
可
its
以
various
这个
details.
进去
As
看
we
基
can
站的
say,
详情。我们
Node
基
Bs
站
can
呢，
be
它通过
categorized
这个
based
分
on
布
their
方式啊，设备
synchronized
型号、
modes,
基站类型等等，
models,
有分布不
types,
同的类
and
型。
more. We can also look
当
into
然
the
呢，我们也
properties
可以
of each
去看
individual
这些
model.
每一个东西，
For
每一个
instance,
模型
the
会有
radio
一个
unit and distributed unit models
我们可以
have
看到这个天线
fewer
呢，就是现在
properties,
是
while
受
the
控
antenna
属性。
unit model has
那么两个是较
significantly
少的。
more.
我们也可以去看
We
这
can
个
also
基站
explore the
它的属
properties
性，
and
以
actual
及这个
data
基
of
站
G
它的
Node
属性。
Bs, which are the 5G equivalent of Node Bs.
我们也可以
The
快速地对
TESSERACT
这个
DPE provides exceptional
可以
performance,
反应时间的
offering near zero latency while querying or browsing data. This
那么这
allows
样子呢，
all
我们就可
RAN-related
以
data to be
迅速
collected
地把
into
所
an
有的
object model
信息和
database for centralized
全部的
management
收
and
入到
use.
我们的这个数据库当中来。当我们把
With
这
this,
些
we can query data and
数据
feed results into
通
the
过这个方
TESSERACT's
法进行
visualization
最后的
components.
可视化
These
和
tools
这个
enable
来
users to interact
进行
with,
绑定以后呢，我
explore,
们
and
对这
gain
些数据
insights from the
进行
network.
可视化的操作，获得
We
这
can
些
further integrate TESSERACT's built-in AI models and algorithms for advanced
那
data
么我们也
processing.
可以
This
把
enables
该这
predictive
些算法把这
analytics,
些数据
business
对
intelligence,
来
and
进行
network
搜索分
optimizations.
析，来找
For
到一些
instance,
说
we
到了
can
非常重要的
analyze
时候，
network
那么
impact
根
and
据这个
service
网络的构
disruptions
成
down to
来
the
推导
individual
这
user
个
level,
故障会对网络产生
perform
什么样的影
end-to-end
响，
root cause
会有什么样的
analysis
用户的
when
这个
anomalies
这
are
些
detected.
就可以
All of these use cases
精
can be
准地
derived from the object model graph
这样子
and
就
implemented through advanced analytics and AI
和
models.
这张图